Here's something that might surprise you. Earth might not be the best planet for life in the universe. In fact, scientists have found several planets out there that could potentially be even more habitable than our own homeworld. I know what you're thinking. Earth is pretty great, right? We have liquid water, breathable air, a protective magnetic field, and billions of years of stable conditions that allowed life to evolve and thrive. How could anything be better than that? But here's the thing. Earth isn't perfect. Not even close. We have ice ages, we have mass extinctions, we have extreme deserts and frozen wastelands where nothing can survive. Our sun is slowly getting hotter, which means Earth's habitable lifetime is limited, and we're just one big asteroid or super volcano away from a catastrophic event that could wipe out most life. Scientists have started asking a fascinating question: what would a perfect planet for life actually look like? And as we've discovered thousands of planets orbiting other stars, we found some that check more boxes than Earth does. Planets that are bigger, which means more land area and more stable climates. Planets orbiting stars that live much longer than our sun, giving life billions of extra years to evolve. Planets with conditions that might be even better for complex life than what we have here. Today, we're going to explore these worlds. We'll look at what makes a planet habitable in the first place, why Earth isn't the perfect template, and which planets out there might actually be better homes for life than Earth is. Some of these worlds are only a few dozen light years away. They're out there right now, possibly covered in oceans, possibly with life already thriving on them, and who knows, maybe one day humans will visit these worlds and discover that Earth was just practice, that the universe saved the really good planets for when we were ready to find them. Let's start with the basics. Before we talk about planets that might be better than Earth, we need to understand what makes a planet habitable in the first place. And the answer is more complicated than you might think. The most basic requirement is liquid water. As far as we know, life needs water. Not ice, not steam, but liquid water, where molecules can move around and interact. Every living thing on Earth needs water to survive. Our cells are mostly water. All the chemical reactions that keep us alive happen in water. Water is the universal solvent. It can dissolve more substances than any other liquid, which makes it perfect for the complex chemistry of life. So for a planet to be habitable, it needs to be at the right temperature for liquid water to exist. Not so hot that water boils away. Not so cold that it freezes solid. There's a sweet spot called the habitable zone, sometimes called the Goldilocks zone, where conditions are just right. But temperature isn't just about distance from the star. It also depends on the planet's atmosphere. Venus is a good example. It's actually closer to the habitable zone than you might think, but it has a runaway greenhouse effect. Its thick atmosphere traps so much heat that the surface temperature is hot enough to melt lead about 900 degrees Fahrenheit. Meanwhile, Mars is on the outer edge of our habitable zone, but it has almost no atmosphere, so it's frozen. So a habitable planet needs the right kind of atmosphere. Not too thick, not too thin. An atmosphere does several important things. It keeps the planet warm through the greenhouse effect, which isn't bad in the right amount. It protects the surface from harmful radiation and meteorites. It helps distribute heat from the day side to the night side, and from the equator to the poles. Without an atmosphere, you get extreme temperature differences that make life really difficult. The atmosphere also needs to have the right composition. You need some greenhouse gases to keep the planet warm, but not too much. Earth's atmosphere is about 78 nitrogen, 21 oxygen, and 1 other gases, including carbon dioxide and water vapor. The oxygen is actually produced by life. It wasn't in the original atmosphere, but the nitrogen and the small amount of CO2 are crucial for keeping Earth at the right temperature. A planet also needs to be the right size. If it's too small, like Mars, it can't hold on to a thick atmosphere. The The planet's gravity isn't strong enough, and atmospheric gases slowly escape into space. Mars used to have a thicker atmosphere and probably liquid water on its surface, but over billions of years, it lost most of its atmosphere. If a planet is too big, gravity becomes a problem for a different reason. Super strong gravity would make it really hard for life to evolve. Imagine trying to move around if you weighed 3 times what you do now. Flying would be almost impossible. Trees couldn't grow very tall because they'd collapse under their own weight, but we'll come back to this because some super-Earths might actually have advantages despite the higher gravity. A planet needs to be geologically active. Earth has plate tectonics. The crust is divided into plates that slowly move around, creating mountains, volcanoes, and ocean trenches. This might seem destructive, and it can be, but it's actually crucial for life. Plate tectonics recycles carbon dioxide. CO2 gets locked up in rocks, those rocks get subducted into the mantle, and then the CO2 gets released through volcanoes. This creates a natural thermostat that keeps Earth's climate relatively stable over billions of years. Without plate tectonics, a planet could end up with too much CO2 in the atmosphere, causing a runaway greenhouse effect like Venus, or all the CO2 could get locked up in rocks, making the planet too cold. Earth's plate tectonics help maintain that balance. A magnetic field is also important. Earth has a strong magnetic field generated by its liquid iron core. This field deflects dangerous particles from the sun called the solar wind. Without this protection, the solar wind would slowly strip away our atmosphere, just like what happened to Mars when its magnetic field shut down billions of years ago. The magnetic field also protects life on the surface from harmful radiation. The planet needs to orbit the right kind of star. Our sun is a yellow dwarf star, medium-sized, stable, and long-lived. It's been burning steadily for 4.6 billion years, and will continue for another 5 billion years. That's a long time for life to evolve and develop. If Earth orbited a massive blue star, the star would only live a few million years before exploding. That's not enough time for complex life to evolve. On the other hand, red dwarf stars, the smallest, coolest stars, live for trillions of years. That sounds great, but red dwarfs have problems. They tend to have violent flares that blast their planets with radiation. They're also so dim that a planet would need to orbit really close to be warm enough, and at that distance, the planet would probably become tidally locked one side, always facing the star, one side always dark. That creates extreme temperature differences that could be bad for life. The planet also benefits from having a large moon like ours. Earth's moon stabilizes our axial tilt, the angle at which Earth is tilted. Without the moon, Earth's tilt would vary wildly over time, causing dramatic climate swings. The moon also creates tides, which might have been important for early life. Tidal pools could have been places where the chemistry of life first developed. And finally, the planet needs time. Life on Earth started simple, just single-celled organisms about 3.8 billion years ago, but it took another 3 billion years for complex multicellular life to appear. Intelligence took even longer. Humans only showed up in the last few 100,000 years. For a planet to develop complex, intelligent life, it probably needs billions of years of stable conditions. So when we talk about a habitable planet, we're not just talking about a rock in the right orbit. We're talking about a complex system with the right size, the right atmosphere, the right amount of water, geological activity, a magnetic field, a stable star, and billions of years of relative stability. It's a long checklist. Earth checks most of these boxes, but as we're about to see, it doesn't check all of them perfectly, and some planets out there might actually do better. Let's talk about Earth's flaws. I'm not trying to trash our home planet. Earth is obviously pretty great since we're here talking about it, but if you were designing a planet from scratch to be the absolute best home for life, you probably wouldn't make it exactly like Earth. First, let's talk about Earth's habitability over time. Our planet has been habitable for about 4 billion years, which sounds impressive, but it won't last forever. The sun is slowly getting brighter and hotter. In about 1 billion years, maybe 1.5 billion at Earth will become too hot for life to survive. The oceans will evaporate, we'll lose our water to space, and Earth will become a dead, dry world like Venus. Now, 1 billion years is a long time, but it's not that long in cosmic terms. The Sun will live for about 10 billion years total. Earth is only habitable for about half of our Sun's lifetime. That's not terrible, but we can do better. Some planets orbit stars that will stay stable and habitable for much longer. Second, Earth's climate isn't as stable as you might think. We've had multiple ice ages, where much of the planet was covered in glaciers. During these ice ages, the habitable zone on Earth shrinks dramatically. There have also been hothouse periods where the planet was much warmer, with no ice even at the poles. These climate swings make life harder. Then, there are mass extinction events. Earth has had at least 5 major mass extinctions, where the majority of species died out. The most famous is the asteroid that killed the dinosaurs 66 million years ago, but there have been worse ones. The Permian extinction, 252 million years ago, killed about 96 of all marine species and 70 of terrestrial species. Life barely survived. These extinctions are caused by various things: asteroid impacts, massive volcanic eruptions, sudden climate changes, but they show that Earth isn't perfectly stable. Life here is always one disaster, away from being mostly wiped out. Earth's size is decent, but it could be better. Our planet has limited land area. About 71% of Earth's surface is covered by oceans. That leaves only 29% as land, and much of that land is desert, frozen tundra, or mountains where life struggles. The actual habitable land area is pretty small. A larger planet with the same ocean-to-land ratio would have much more space for life to thrive and diversify. Our magnetic field is strong, which is good, but it's not permanent. Earth's magnetic field has flipped many times in the past. North becomes south, south becomes north. During these flips, which can take thousands of years, the magnetic field weakens significantly. During these periods, Earth gets less protection from solar radiation. Some scientists think mass extinctions might be linked to magnetic field reversals, though this is still debated. Worse, the magnetic field could potentially shut down completely, like it did on Mars. We don't think that will happen anytime soon, but it's not impossible. If Earth's core stopped generating a magnetic field, we'd slowly lose our atmosphere to the solar wind, just like Mars did. Earth's orbit isn't perfectly circular. It's close to circular, but there's a slight ellipse. This means we're a bit closer to the Sun at some times of year than others. Combined with Earth's axial tilt, this contributes to seasons. Seasons aren't necessarily bad. They create diversity and different ecological niches, but they also create stress for organisms that have to adapt to changing conditions. A planet with a more perfectly circular orbit and less axial tilt would have a more stable climate year-round. Our solar system's position in the galaxy isn't optimal either. We're in a decent spot not too close to the galactic center, where there's lots of radiation and gravitational disruption, not too far out, where there aren't enough heavy elements to form rocky planets. But we're not in the absolute safest zone. Earth has been hit by nearby supernovas in the past. These distant explosions send out waves of radiation that can affect Earth's atmosphere and possibly contribute to extinction events. Earth's plate tectonics, while generally helpful, can also cause problems. Earthquakes, volcanic eruptions, and tsunamis are all consequences of plate tectonics. These events can be devastating for life in affected areas. A planet with more stable, gentler geological activity might be safer for surface life while still maintaining the carbon cycle. Our Sun, while stable by star standards, does have solar flares and coronal mass ejections. These bursts of radiation and particles can damage satellites, disrupt communications, and in extreme cases could harm life on the surface. A planet around an even more stable star would face less of this risk. Earth doesn't have enough land at optimal latitudes. The equator gets the most sunlight and is generally warm year-round, but much of the tropical land area is rainforest, where the soil isn't great for agriculture. The temperate zones, which are ideal for complex land life, are relatively narrow bands. A planet with less axial tilt would have wider temperate zones, making more of the planet comfortable for life. Water is crucial for life, but you can have too much of a good thing. If Earth's oceans were much deeper or covered more of the surface, there might not be enough land for complex terrestrial life to evolve. Conversely, if we had less water, we'd have more land, but possibly less climate stability since oceans help regulate temperature. Earth's water amount is okay, but it's not necessarily optimal. Our moon is great for stabilizing our axial tilt, but it's slowly moving away from Earth. It's drifting away at about 1.5 inches per year. Eventually, in the far future, the moon will be too far away to stabilize Earth's tilt effectively. That will lead to wild climate swings that could make Earth less habitable. And finally, there's the oxygen problem. This might sound weird because we need oxygen to breathe, but Earth's atmosphere has way more oxygen than is strictly necessary for life. We have 21 oxygen in our atmosphere. Most complex life could function fine with 15 or even 10. The problem with high oxygen is that it makes fires much more intense and frequent. Forest fires are natural, but they're more devastating in a high oxygen atmosphere. In Earth's past, during the Carboniferous period about 300 million years ago, oxygen levels reached 35. Insects grew to massive sizes, dragonflies with wingspans of over 2 feet because they could absorb more oxygen, but fires were also much more common and intense. A planet with slightly less oxygen might actually be safer for terrestrial life while still supporting respiration. Now, I want to be clear, none of these issues make Earth a bad planet for life. Obviously, it's good enough for life to thrive. We're here, after all. But the point is that Earth isn't the ultimate perfect template for a habitable planet. It's just one example of what works. And when we look at other planets, we find some that might actually have advantages Earth doesn't have. A more habitable planet would be larger than Earth, giving more land area. It would orbit a more stable star that lives longer, extending the habitable period. It would have a thicker atmosphere for better radiation protection and climate stability. It would have a perfect balance of land and ocean. It would have stronger, more permanent magnetic field. It would be in a safer region of the galaxy, and it would have billions of extra years of habitable conditions. And here's the exciting part. We found planets that might have some or even many of these advantages. Before we dive into specific planets, let's talk more about this idea of the habitable zone. It's not as simple as you might think. The traditional definition of the habitable zone is the range of distances from a star where liquid water can exist on a planet's surface. If you're too close to the star, it's too hot and water evaporates. Too far away, it's too cold and water freezes. In between, you're in the habitable zone where water stays liquid. For our solar system, the habitable zone extends from about 0.95 AU to about 1.4 AU. 1 AU, or astronomical unit, is the distance from Earth to the Sun, about 93 million miles. So Earth sits at 1 AU, right in the middle of the habitable zone. Venus is at 0.72 AU, too close and too hot. Mars is at 1.5 AU, right on the outer edge, which is why it's cold, but might have had liquid water in the past when it had a thicker atmosphere. But here's where it gets complicated. The habitable zone isn't a fixed thing. It depends on many factors. First, it depends on the star's temperature and brightness. Hotter, brighter stars have habitable zones that are farther out. Cooler, dimmer stars have habitable zones that are closer in. A red dwarf star, which is much cooler than our sun, might have its habitable zone at 0.1 AU or even closer. That means a habitable planet around a red dwarf would orbit much faster, maybe completing a full orbit in just a few weeks. The habitable zone also changes over time. Stars get brighter as they age. Our sun was about 30 dimmer 4 billion years ago when life first appeared on Earth. That means the habitable zone was closer to the sun back then. Mars might have been right in the middle of it, which is why we think Mars had liquid water early in its history. But as the sun brightened, the habitable zone moved outward. Mars fell out of the habitable zone and froze. In about 1 billion years, Earth will be on the inner edge of the habitable zone and getting too hot. The habitable zone also depends on the planet's atmosphere. A planet with a thick atmosphere and lots of greenhouse gases can stay warm, even if it's farther from the star. Conversely, a planet with little to no atmosphere will be cold, even if it's close to the star. So the habitable zone is really more like a habitable region that varies depending on what kind of planet you're talking about. There's also the concept of the continuously habitable zone, or CHZ. This is the region where a planet can maintain liquid water on its surface throughout the entire main sequence lifetime of its star. For our sun, the CHZ is narrower than the habitable zone, maybe only from about 0.99 AU to 1.01 AU. Earth is technically just barely in the CHZ. We've been habitable for 4 billion years, and might stay that way for another 1 billion, but that's only about half the sun's 10 billion year lifespan. A planet at exactly 1.0 AU from a sun-like star would be right in the center of the CHZ and could potentially stay habitable for the star's entire life. Or better yet, a planet around a smaller, cooler star that lives much longer might have even more time in the CHZ. There's also something called the optimistic habitable zone versus the conservative habitable zone. The conservative estimate only includes planets that are very likely to have liquid water, basically Earth-like planets with Earth-like atmospheres. The optimistic estimate includes planets that might have liquid water under different conditions, maybe with thicker atmospheres or with different compositions. For example, Titan, Saturn's largest moon, is way outside the traditional habitable zone. The surface temperature is about 290 degrees Fahrenheit, but Titan has lakes and rivers of liquid methane. It's not water, but it's liquid. Some scientists have speculated that life might be possible in liquid methane at very low temperatures, using completely different chemistry than life on Earth. If that's possible, then the habitable zone becomes much wider. Some scientists have proposed the concept of a galactic habitable zone too. This is the idea that there are regions of the galaxy that are better for life than others. Too close to the galactic center, and you get too much radiation from nearby supernovas, black holes, and dense star clusters. Too far from the center, and there might not be enough heavy elements like carbon, oxygen, and iron to form rocky planets. Earth is in what seems to be a good spot in our galaxy about 26,000 light-years from the center, in a relatively quiet region between spiral arms. But there might be even better spots. Some regions of the galaxy might have more stable conditions, fewer nearby supernovas, and better concentrations of heavy elements. There's also the question of moons. We usually think about planets being in the habitable zone, but moons can be habitable too. Jupiter's moon Europa probably has a global ocean of liquid water beneath its icy crust. Saturn's moon Enceladus probably does too. These oceans are kept liquid by tidal heating. The gravitational pull of their parent planets flexes the moons, generating heat from friction. Europa and Enceladus are nowhere near the sun's habitable zone in the traditional sense, but they might have habitable environments beneath their ice. A large moon orbiting a giant planet in the habitable zone could potentially be even more habitable than a regular planet because it gets additional tidal heating. The habitable zone concept is useful, but it's also simplified. Real habitability depends on dozens of factors: the planet's size, its atmosphere, its magnetic field, its geological activity, its orbit, the star it orbits, where it is in the galaxy, and more. Two planets at exactly the same distance from the same type of star could have completely different climates and habitability depending on these other factors. When scientists search for potentially habitable planets, they start by looking in the habitable zone because that's the easiest place to look. But they know that being in the habitable zone doesn't guarantee habitability, and being outside, it doesn't rule it out entirely. With that understanding, let's look at some specific planets that might be more habitable than Earth. One of the most interesting categories of potentially super habitable planets is what we call super-Earths. These are rocky planets that are larger than Earth, but smaller than Neptune. Typically, we're talking about planets with 1.5 to 2.5 times Earth's radius and anywhere from 2 to 10 times Earth's mass. When we first started discovering these planets, scientists weren't sure what to make of them. We don't have anything like them in our solar system. Mercury, Venus, Earth, and Mars are all relatively small. Jupiter, Saturn, Uranus, and Neptune are all gas or ice giants. There's nothing in between, but super-Earths turn out to be incredibly common in the galaxy. They might actually be the most common type of planet. At first glance, you might think a bigger planet with stronger gravity would be worse for life. And there are definitely downsides. If you weighed 150 pounds on Earth, you might weigh 300 or even 400 pounds on a super-Earth. That's a lot. It would be exhausting to move around. Climbing stairs would be brutal. Flying would be much harder. Birds might not be able to exist, and forget about human flight. But there are also some major advantages to being a super-Earth. First, more surface area. A planet that's twice Earth's radius would have 4 times the surface area. That's 4 times as much land and ocean, 4 times as much space for ecosystems to develop, 4 times as many different environments where life could adapt and diversify. If the planet has a similar ratio of land to ocean as Earth, that's 4 times as much habitable land. More land means more biodiversity. On Earth, biodiversity tends to be higher in larger areas. Bigger islands have more species than smaller islands. Bigger continents have more ecosystems. A super-Earth with 4 times the surface area could potentially support far more species and far more complex ecosystems than Earth does. Second, geological stability. Larger planets retain their internal heat longer. Earth's core is still liquid and hot after 4.6 billion years, generating our magnetic field and driving plate tectonics. But smaller planets like Mars cool down much faster. Mars's core solidified, shutting down its magnetic field billions of years ago. A super-Earth would stay geologically active even longer than Earth. It would have plate tectonics for more of its lifetime, keeping its carbon cycle active and climate stable. Its magnetic field would be stronger and last longer, providing better protection from stellar radiation. This means a super-Earth could potentially stay habitable even longer than Earth, maybe for the entire lifetime of its star. Third, atmosphere retention. A bigger planet with stronger gravity can hold on to its atmosphere better. This is especially important for lighter gases like hydrogen and helium, but it also means the planet is less likely to lose water to space over billions of years. Earth loses a tiny amount of atmosphere to space constantly, but it's so slow that it doesn't matter on human timescales. A super-Earth would lose even less. A thicker atmosphere also provides better protection from radiation and meteorites. Small meteorites that would hit Earth's surface would burn up in a super-Earth's thicker atmosphere. Harmful ultraviolet and X-ray radiation from the star would be better absorbed. This makes the surface safer for life. Fourth, climate stability. A larger planet with more water would have more thermal inertia. Water is really good at absorbing and storing heat. Oceans act as giant heat batteries, warming up slowly and cooling down slowly. This smooths out temperature variations. A super-Earth with deep oceans would have very stable temperatures, with less dramatic seasons and fewer temperature extremes. Now, there are definitely challenges for life on super-Earths. The higher gravity would make certain things harder. As I mentioned, flight would be more difficult. Trees probably couldn't grow as tall because they'd collapse under their own weight. Mountains would be smaller because rock can only support so much weight before it flows, like a very slow liquid. Animals would need to be sturdier. Tall creatures would be at a disadvantage. Life would probably trend toward being more compact and low to the ground. But that doesn't mean life couldn't thrive. It would just be different. Whales are huge, despite Earth's gravity, because water supports their weight. A super-Earth with extensive oceans might have incredibly large marine life, even if land life was more compact. One concern some scientists had was that super-Earths might have so much gravity that plate tectonics wouldn't work. The crust might be too heavy to subduct into the mantle, but computer simulations suggest this isn't a problem. Plate tectonics should still work on super-Earths, maybe even better than on Earth, because there's more internal heat driving the process. Another potential issue is water. If a super-Earth has too much water, it could be a water world with no exposed land at all. The entire surface would be ocean, possibly hundreds of miles deep. That's not necessarily bad for life. Oceans are full of life on Earth, but it would preclude land-based life and technological civilization as we know it. There's also the question of whether a super-Earth would have a large moon for tilt stabilization. Our moon formed from a collision between proto-Earth and another planet-sized object very early in solar system history. Would the same thing happen around a super-Earth? Maybe, maybe not. But perhaps super-Earths don't need their tilt stabilized as much. With more mass and more rotational inertia, they might be naturally more stable. One super-Earth that's gotten a lot of attention is Kepler 442b. This planet is about 1/200 light-years away. It's roughly 1.3 times Earth's radius and orbits a K-type star, slightly cooler and smaller than our Sun once every 112 days. It's right in the middle of the habitable zone. Computer models suggest Kepler 4e42b is probably rocky and might receive about 70 of the light that Earth gets from the Sun. That sounds dim, but with the right atmosphere, it could maintain liquid water on its surface. The planet's star is cooler and more stable than our Sun, and it will live much longer, maybe 20 to 30 billion years. That means Kepler 442b could potentially be habitable for far longer than Earth. Another interesting one is Kepler 452b, sometimes called Earth's bigger, older cousin. It's about 1.6 times Earth's radius and orbits a Sun-like star once every 385 days, very close to Earth's year. The planet is in the habitable zone and probably receives similar amounts of starlight to what Earth gets. The catch? It's about 1,400 light-years away, and we don't know for certain if it's rocky or a small gas planet. If Kepler 452b is rocky, it could have about 5 times Earth's mass. That would make gravity about 2.5 times stronger than Earth's. Heavy, but not impossible for life, and the planet's star is older than our Sun, about 6 billion years old, compared to 4.6 billion. If the planet formed around the same time as its star, it's had 1.5 billion extra years for life to evolve. Then, there's K218b, which we talked about in another video. It's about 2.6 times Earth's radius and orbits a red dwarf star. It's in the habitable zone, and the James Webb Space Telescope detected possible signs of biological activity in its atmosphere, though this is still being debated. K218b might be a Hycean world, a planet with a hydrogen-rich atmosphere over a global ocean. If so, it represents a type of habitable planet completely different from Earth. There are dozens of other super-Earths in habitable zones that we've discovered. Most of them are too far away to study in detail with current telescopes. We can tell their size and orbit, but we can't yet determine if they have atmospheres, what those atmospheres are made of, or if there's water on the surface. But statistically, some of them almost certainly do, with thousands of super-Earths discovered and likely billions more in the galaxy. galaxy, it would be shocking if none of them were habitable, and given their advantages, more surface area, better atmosphere retention, longer habitability, more stable climate, some of them might not just be habitable, but more habitable than Earth. The big question is whether complex life could evolve on a super-Earth despite the higher gravity. Most scientists think yes. Life is incredibly adaptive. If Earth life could adapt to the deep ocean, to frozen Antarctica, to boiling hot springs, to extreme pressure, then alien life could surely adapt to higher gravity if that's all it ever knew. In fact, some scientists speculate that super-Earths might be better for complex life than Earth is. The higher gravity would keep the atmosphere thick and protective. The longer geological activity would maintain stable conditions for billions of extra years. The larger surface area would support more biodiversity. These planets would give life more space, more time, and more stability to develop. If we're looking for life in the universe, super-Earths might be our best bet. Red dwarf stars, also called M-dwarfs, are the most common type of star in the galaxy. About 75 of all stars are red dwarfs. They're small, cool, and incredibly long-lived. While our sun will last about 10 billion years total, red dwarfs can last for trillions of years. Some red dwarfs that formed at the beginning of the universe are still in their infancy, and they'll still be burning long after our sun has died. From a habitability standpoint, this longevity is really appealing. A planet in the habitable zone of a red dwarf could potentially stay habitable for an incredibly long time. Earth has maybe 1 billion years of habitability left. A planet around a red dwarf could have trillions of years, but red dwarfs have some serious problems that might make their planets less habitable. First, red dwarfs are dim. They're so cool that they barely glow compared to our sun. To receive enough light and heat to stay warm, a planet would need to orbit very close, maybe only a few million miles away, compared to Earth's 93 million miles from the sun. At that distance, a planet's orbit might take only a few days or weeks. Orbiting so close causes a problem called tidal locking. Just like Earth's moon always shows us the same face, because it's tidally locked to Earth, a planet this close to its star would become tidally locked to the star. One side of the planet would always face the star in perpetual daylight. The other side would always face away in eternal night. This creates extreme temperature differences. The day side might be scorching hot, the night side might be frozen solid. All the water on the day side would evaporate. All the water on the night side would freeze. Life would have to exist in the narrow twilight zone between day and night, where temperatures are moderate. However, some computer models suggest that if the planet has a thick atmosphere, wind patterns might distribute heat from the day side to the night side, making the whole planet more habitable. The atmosphere would act like a heat transport system, keeping the night side warm enough to prevent everything from freezing. So tidal locking might not be a deal breaker if the planet has the right atmospheric conditions. The second problem with red dwarfs is stellar flares. Young red dwarfs are extremely active. They produce powerful flares, sudden bursts of radiation that are far more intense than anything our sun produces. These flares can be thousands of times more powerful than solar flares and happen much more frequently. A planet in the habitable zone of a red dwarf would be so close that these flares could strip away its atmosphere over time. The radiation would also be harmful to any life on the surface. This makes young red dwarf systems pretty hostile to life. But here's the good news. Red dwarfs calm down as they age. After a few billion years, they settle into a much more stable state with fewer and weaker flares. So planets around older red dwarfs might be perfectly fine for life. There's also the possibility of life adapting to the harsh radiation. Life on Earth exists in extreme radiation environments like the upper atmosphere and high-altitude mountains. Some organisms can survive levels of radiation that would kill humans instantly. Alien life that evolved around a red dwarf might be naturally resistant to radiation that would be deadly to Earth life. Despite these challenges, we found some really interesting, potentially habitable planets around red dwarfs. The most famous is Proxima Centauri b. This planet orbits Proxima Centauri, the closest star to our solar system, just 4.2 light-years away. Proxima b is probably a little more massive than Earth and orbits its star every 11 days. It's right in the habitable zone. Proxima Centauri is a red dwarf, so all the problems we discussed apply. It's a flare star, very active, with frequent powerful flares. Proxima b is tidally locked, but it's so close to us that if there's any chance of visiting another star system in the future, this would be the first target. And if Proxima b has the right atmosphere, it might be habitable despite its challenges. Then there's the TRAPPIST-1 system, which might be the most exciting planetary system we've discovered. TRAPPIST-1 is a red dwarf about 40 light-years away. It has 7 Earth-sized planets, and at least 3 of them are in the habitable zone. The planets are named TRAPPIST-1e, F, and G, and they're all rocky worlds that might have liquid water. What makes TRAPPIST-1 special is that all 7 planets are close together. The entire system could fit inside the orbit of Mercury. The planets are so close that if you stood on one, you'd be able to see the others in the sky, some appearing larger than our moon does from Earth. It's like a science fiction dream, a solar system where you could potentially visit multiple habitable worlds without traveling interstellar distances. TRAPPIST-1 is an older, quieter red dwarf, so it doesn't have the extreme flare activity of younger stars. Computer models suggest that at least some of the planets could have atmospheres and liquid water. The James Webb Space Telescope is currently studying these planets to see if we can detect atmospheres and maybe even signs of life. Another interesting system is Gliese 667 cc. This planet orbits a red dwarf in a triple star system about 24 light-years away. It's probably a super-Earth with about 4 times Earth's mass. It orbits its star every 28 days and is right in the middle of the habitable zone. If it has the right atmosphere, it could be quite habitable. Red dwarf planets have one major advantage over planets around sun-like stars: abundance. With 3 out of every 4 stars being red dwarfs, there are potentially billions of Earth-sized planets in habitable zones around red dwarfs in our galaxy alone. Even if only a small percentage of them are actually habitable, that's still a lot of habitable worlds. Some scientists have even argued that red dwarf planets might be the most common abode for life in the universe. Yes, they have challenges, but they're so numerous and their stars last so long that they could dominate the statistics. There's also something poetic about red dwarfs lasting trillions of years. Long after our sun has burned out and Earth is gone, planets around red dwarfs will still be habitable. If life evolves on these worlds and becomes intelligent, those civilizations could potentially last for incomprehensible amounts of time. While Earth's civilization has existed for only a few thousand years, and our planet will be habitable for maybe 1 billion more, a civilization around a red dwarf could potentially last for hundreds of billions or even trillions of years. In the very long run, the deep future of the universe, red dwarf planets might be the only habitable worlds left. All the sun-like stars will have burned out. Only the red dwarfs will remain, slowly burning their hydrogen fuel at barely perceptible rates, keeping their planets warm for eons beyond anything we can imagine. So while red dwarf planets face challenges, they might ultimately be the most important habitable worlds in the universe simply because they'll be the last ones standing. So far, we've talked mostly about planets that are similar to Earth rocky worlds, with a mix of land and ocean, but there's another category of potentially habitable planet that's completely different: ocean worlds. An ocean world is a planet that's covered entirely, or almost entirely, by liquid water. No continents, no islands, just a global ocean that might be hundreds or even thousands of miles deep. These worlds are sometimes called water worlds or aqua planets. At first, this might sound like a paradise. Earth's oceans are teeming with life. Imagine a whole planet that's nothing but ocean. But ocean worlds actually present some interesting challenges and opportunities. Let's start with how they form. When planets form from the disk of gas and dust around a young star, they accumulate various materials. Close to the star where it's hot, you get mostly rock and metal. Farther out where it's cold, you get lots of ice along with the rock. This is why the inner planets in our solar system are rocky, while the outer planets are ice and gas giants. Sometimes, though, a planet that forms in the cold outer reaches of a solar system can migrate inward toward the star. This happens through gravitational interactions with other planets, or with the disk of material. As this icy planet moves into the warmer inner region, all that ice melts, and you end up with a world covered in a thick layer of water. Earth actually has a pretty small amount of water compared to what's possible. Water makes up less than 0.1 of Earth's mass. On an ocean world, water might make up 10, 20, or even 50 of the planet's mass. We're talking about oceans that are hundreds of miles deep, so deep that the pressure at the bottom would turn water into exotic forms of ice, despite the temperature being hot enough to boil it normally. One of the most interesting candidates for a water world is K2-18b, which we've mentioned a few times. This planet is about 120 light-years away and is about 2.6 times Earth's radius. Recent observations suggest it might have a hydrogen-rich atmosphere over a global ocean. If that's true, it would be our first confirmed water world. Another candidate is GJ1214b, which orbits a red dwarf about 48 light-years away. It's about 2.7 times Earth's radius, and probably has a very thick atmosphere. Scientists aren't sure if it's a small gas planet or a water world with a steamy atmosphere, but it's definitely one of the most intriguing planets we've found. Towai 1452b is another potential water world discovered in 2022. It's about 100 light-years away, orbits a red dwarf every 11 days, and is about 70 larger than Earth. Based on its density, scientists estimate that up to 30 of its mass could be water. That's an insane amount, 300 times more water than Earth has relative to size. So what would life be like on an ocean world? Well, there obviously wouldn't be any land-based life. Everything would be aquatic. But that doesn't mean life couldn't thrive. Earth's oceans are full of incredible biodiversity, from microscopic plankton to giant whales, from coral reefs to deep-sea vents. Ocean life is diverse and complex. A planet that's entirely ocean could potentially support an enormous variety of marine life. The big question is, could complex, intelligent life evolve on an ocean world? On Earth, intelligence evolved on land. Humans, other primates, elephants, parrots, crows. All the really smart animals are terrestrial, or at least semi-terrestrial. Dolphins and whales are very intelligent, but they evolved from land animals and secondarily adapted to the ocean. This raises an interesting question. Does intelligence require land? Is there something about the terrestrial environment that promotes the evolution of complex brains and tool use? One argument is that fire and technology require air. You can't have fire underwater, and without fire, you can't smelt metals, make ceramics, or develop most technologies. An aquatic civilization, no matter how intelligent, would be limited in what they could build. But maybe that's just Earth-centric thinking. Maybe there are other paths to technology that don't require fire. Maybe an ocean civilization could develop biotechnology using engineered organisms instead of machines. Maybe they could discover chemistry and physics through different means. Or maybe intelligence is less likely to evolve on ocean worlds, making them habitable, but less likely to host civilizations. This is one of many unknowns. There's also the question of what's below the Ocean. On a water world with an extremely deep ocean, the pressure at the bottom would be enormous, millions of times greater than at sea level. Under these pressures, water behaves strangely. It can form different types of ice that exist at high temperatures. You could have hot ice at the bottom of the ocean ice that's hundreds of degrees Fahrenheit, but solid because of the pressure. Below the ocean might be a layer of this exotic ice, and below that, a rocky core, but surface life would never have access to that rock. All the minerals and elements needed for life would need to be dissolved in the ocean or brought up by geological activity. Some scientists have suggested that water worlds might have active ocean floor volcanism. Just like Earth has undersea volcanoes and hydrothermal vents, a water world might have similar features. These vents could provide energy and nutrients for life. On Earth, some of the most extreme ecosystems exist around deep-sea vents, supporting life in complete darkness using chemicals from the planet's interior. A water world's ocean might have distinct layers. Near the surface where sunlight penetrates, you'd have photosynthetic life, the equivalent of algae and plankton. In the middle depths, you'd have organisms that feed on material falling from above. In the deepest parts, you might have vent-based ecosystems. One advantage of water worlds is climate stability. Water is really good at storing heat and distributing it around the planet. A global ocean would have very stable temperatures with no extreme weather, no hurricanes or storms the way we have them, because those are driven by temperature differences between land and ocean. An ocean world would have gentle, consistent conditions perfect for life. There's also no danger of running out of water. Earth's water can get locked up in ice ages or lost to space over billions of years. A water world has so much water that this isn't a concern. The main disadvantage, beyond the lack of land, is the depth. If the ocean is thousands of miles deep, only the top fraction of it would be truly habitable. Light only penetrates the top few hundred feet. Below that, it's dark. And as you go deeper, pressure increases until conditions become extreme. But even with these limitations, ocean worlds could be incredibly habitable, maybe even more consistently habitable than Earth. Earth's land masses go through dramatic climate changes. Deserts expand and contract. Ice ages cover continents. But a global ocean would maintain stable conditions for billions of years. We don't know how common water worlds are yet. It depends on how often planets migrate inward and how much ice they carry, but some models suggest they could be quite common, maybe as common as Earth-like rocky planets with mixed land and ocean. If that's true, then a significant fraction of habitable planets in the universe might be ocean worlds. And if life is common in the universe, a lot of that life might be swimming rather than walking. So how do we actually find these potentially super habitable planets? It's not easy. Most of them are hundreds or thousands of light years away, orbiting distant stars. They don't emit light of their own, and they're so small and dim compared to their stars that we can't just point a telescope at them and take a picture. Instead, astronomers use several clever techniques to detect planets indirectly. The most successful method so far is called the transit method. This is how the Kepler Space Telescope found thousands of planets. Here's how it works. If a planet orbits its star in such a way that it passes directly between us and the star, it blocks a tiny bit of the star's light. The star appears to dim slightly during this transit. The amount of dimming tells us the planet's size. A bigger planet blocks more light, causing a bigger dip in brightness. The time between transits tells us the planet's orbital period. If the star dims every 365 days, the planet takes 365 days to orbit, just like Earth. From the orbital period and knowing the star's mass, we can calculate how far the planet is from its star, and from that, we can figure out if it's in the habitable zone. The transit method has found thousands of planets, including most of the potentially habitable ones we know about, but it has a limitation. The planet's orbit has to be aligned just right for us to see transits. If the orbit is tilted from our perspective, we'll never see the planet pass in front of the star. This means we're only detecting a small fraction of the planets that are actually out there. Another method is the radial velocity method, sometimes called the wobble method. When a planet orbits a star, it doesn't orbit around a fixed point. Both the star and the planet orbit around their common center of mass. For a system like ours, where the planet is much less massive than the star, this center of mass is close to the center of the star, but not exactly at the center. This means the star wobbles slightly as the planet orbits. When the star moves toward us, its light is slightly blue shifted. When it moves away, it's slightly red shifted. By measuring these shifts in the star's spectrum, we can detect the planet. The radial velocity method tells us the planet's mass and orbit. Combined with the transit method, we can figure out both the size and mass, which tells us the planet's density. This is how we know if a planet is rocky like Earth or gaseous like Jupiter. A few planets have been directly imaged, meaning we've actually taken pictures of them. But this only works for very special cases, usually giant planets that are very far from their stars and still hot from formation, making them bright in infrared light. Small, rocky planets in habitable zones are too close to their bright stars to be directly imaged with current technology, but technology is improving rapidly. The James Webb Space Telescope, which launched in 2021, can study the atmospheres of some exoplanets by looking at starlight filtering through the planet's atmosphere during a transit. Different gases absorb light at different wavelengths, creating a unique fingerprint. By analyzing this fingerprint, we can figure out what's in the atmosphere. This is how scientists detected possible signs of life-related gases in K2-18b's atmosphere. JWST saw signs of dimethyl sulfide, a gas that on Earth is only produced by living things. This detection is still being confirmed and debated, but it's exactly the kind of discovery JWST was built to make. Future telescopes will be even more powerful. NASA is planning missions like the Habitable Worlds Observatory, specifically designed to directly image Earth-like planets and study their atmospheres for signs of life. The European Space Agency is developing similar missions. Within the next couple of decades, we should be able to not just find potentially habitable planets, but actually determine if they have the conditions for life. We'll be able to see if they have water vapor in their atmospheres, oxygen, methane, and other potential biosignatures. Finding truly Earth-like planets is still challenging because they're the hardest to detect. They're small, they're in year-long or multi-year orbits, which means transits are infrequent and they're dim. Most of the potentially habitable planets we've found so far are super-Earths or planets around red dwarfs, because those are easier to detect. But we're getting better. We're finding smaller planets in longer orbits. And we're starting to find planets around sun-like stars, not just red dwarfs. Each new generation of telescopes and detection techniques brings us closer to finding a true Earth twin, or more likely, a planet that's even better than Earth for life. The search is accelerating. We've gone from knowing of 0 exoplanets 30 years ago to knowing of over 5,000 today. Many of those are in or near habitable zones, and we've barely scratched the surface. There are likely billions of planets in our galaxy alone. Statistically, some of them must be habitable, and given what we've learned about what makes a planet super habitable, the advantages of being larger, orbiting a more stable star, having a thicker atmosphere, some of those planets are almost certainly more habitable than Earth.